Uh, the last example we're going to do to illustrate Lewis structures and resonance structures is a pretty simple ion called the acetate ion. This is what happens when acetic acid loses a proton. It forms this ion, and it has maybe more atoms in it than our last example, but in terms of reactivity or resonance structures, it's pretty simple. So we'd have to probably have a little more information given to you in order to see how these atoms are connected. Um, we can do a little bit of work here. Let's see, well, we've got this carbon, right? It has 3 hydrogens attached to it. So let's do that. That's why it's a CH3. And then another carbon. And this is where it gets a little confusing. We don't really know, just based on this, where those oxygens are. Is it oxygen and then another oxygen, or both of these oxygens attached to the carbon? You'd have to be given some information about that. But as we'll see, as you get into organic chemistry, the CO2 typically means that both of those oxygens are attached to a carbon. If it was 2 oxygens in series, it would have those separately as O and then O. Okay, so here's the basic framework for our molecule. Let's do our Lewis structure. So we have 3 valence electrons plus 8 from our 2 carbons plus 12 from our 2 oxygens plus 1 because it's negatively charged anion. So this is 11, so that would be 23. And we have a total of 24 valence electrons to work with. We've already used 1, 2, 3, 4, 5, 6 bonds. So 12 electrons are already used. That means we have 12 remaining in order to make everybody happy. How many do we need? Each hydrogen is fine, right? They only need 2 electrons to be happy. This carbon's fine. This carbon is not. It needs 2 electrons, and each of these oxygens needs 6. So that's 6 plus 6 is 12, plus 2, we need 14 electrons if we were to make everyone happy with their own lone pairs. Now, we don't have 14, we have 12, so that means we're going to have some shared electrons. So we're going to add 1 bond to that. Now, like in the previous video, this is where resonance structures come into play. When you have bonds that you're adding, and you have choices of where to add them. Now, I'm not going to be adding that extra bond between the carbon and these hydrogens because that would overload both of those atoms. I'm not going to add the double bond between these 2 carbons because that would overload this carbon. It would exceed its octet. So there's really only 2 choices of where to add that extra bond. One would be between this carbon and that oxygen, and then the other resonance structure would use that double bond between the carbon and the other oxygen. Okay, so let's make sure we did this correctly in terms of Lewis structures. When we add that bond, we have to account for it. So we've used 2 electrons to add that bond. Remember, we had 12, so now we have 10 to work with. And if we did our math correctly, that these 10 electrons should be the perfect number to add as lone pairs to make everybody happy. So again, all of these atoms are happy. Now that we added the double bond, this carbon has its octet. This oxygen needs 6. 1, 2, 3, 4, 5, 6. And this oxygen with a double bond needs 4. So 6 plus 4, that's 10. We're good to go. We used all of our electrons, and we didn't use too many. Okay, so we can fill in the lone pairs on our other structure here. And we can see our 2 resonance structures. Okay, now usually the next step, once you've identified the resonance structures, is to try to rank them, determine which one's more stable, and that's by doing formal charges. Now, the whole left side of these molecules are identical, and so I don't need to assign formal charges to them to be able to discriminate between these two structures. Actually, each of these atoms has a formal charge of 0 anyway. In each of these carbons, my formal charges are 0. The difference is going to be with these oxygens. This oxygen has a formal charge of -1. And since I know that my ion is -1 charge, I know that this final oxygen is going to have a formal charge of 0. Okay. When I assign formal charges on this resonance structure, I see the same sort of pattern. Okay. So the oxygen that has the single bond to the carbon has a -1 formal charge. Everyone else has 0. There's no difference in the total amount of formal charge between these two resonance structures, so that's not going to help me discriminate them. And when I look at and see what atom has the negative charge, both times it's oxygen, which is pretty electronegative. And so there's no difference in which atom has the negative charge either. And so as I try to rank these two resonance structures, I'm not able to. They're equally stable. And really, when we think of the acetate ion and its resonance structures, we sort of consider the locations of those electrons between the carbons as sort of existing back and forth, resonating back and forth between those oxygens, not really preferring one location or the other, but giving a net negative charge to each of those, or to the molecule as a whole.